Welcome. In this session, we'll combine some of the ideas that we had from linear regression and some of the things that we learned about function optimization and try to figure out how steepest descent works for a single artificial neuron. So the way that we'll do this is that we'll have to form a residual function, and then we'll have to have an objective function, and that objective function is what will differentiate to find the direction of steepest descent that we can then use for an iteration. So we'll begin by defining the residual error. So the residual error, and this is an idea that we explored long ago in linear regression, what we'll do is we'll say this is a function of the activation, and we will define that as being the label for the data minus the activation function, which is an activation function of the linear term. Now, there's an additional semicolon W that we should formally put in here, but let's keep it simple now. So that means that the objective function, that is our object, we'll say this is a function of the residual, and we'll define that as, it's traditional to have a 1/2 term because we know a differentiation is coming up. So we'll define that as 1/2 of the residual function squared. So that lets us define the objective. Now, in fact, what we'll do is we'll have many different observations and many different linear responses with corresponding labels. So that means we'll have many of these residuals. So this actually turns into a summation or a vector term. And what this does is now this allows us to go for steepest descent. So the way that we represent the gradient, so in my classes, I represent the gradient as a one form, which is a row-like object. And we'll say that the gradient of this is, so the gradient one form of the objective as a function of the weights of the artificial neuron is, it's a massive application of the chain rule, which looks a little scary, but it's actually really simple, is that it's the derivative of the objective with respect to the residual times the derivative of the residual with respect to the activation times the derivative of the activation with respect to the linear response, and that is multiplied by the derivative of the response with respect to the weight vector. So finally, the weight vector shows up. And what this allows us to do is, here we're using what's called squared error. We could put a different objective in, and that would change this. We could have a different residual, although this is the usual residual. That would change this. If the neuron had a different activation function, it would change this term, and the linear response traditionally does not change. So the direction of steepest descent, which is often slightly incorrectly called gradient descent. The gradient's not a vector, but that's me being my pedantic self. The direction of steepest descent is the direction D, and this is, we take the gradient of the neuron, we transpose it from a row to a column so that it's now a vector, and we negate that, which is what we saw from our simple scalar optimization. And what this will look like is that this derivative is a scalar value, this derivative is a scalar value, this derivative is a scalar value, and this derivative turns out to be a one form. And so what this will look like is that we'll do this transpose. So let's say minus. So what we'll do is we transpose this, so that'll be the derivative of u with respect to w transposed, and then we just go in reverse order, but these are all scalars, so they commute, and there's no big problem. So that's the derivative of the objective with respect to the linear response times the derivative of the residual with respect to the activation times the derivative of the objective with respect to the residual. So there we have it. And what we can do is we can then say, what are these values? So let's do this differentiation. The derivative of f with respect to r is just r, right? When we take this, when we take the derivative of 1/2 r squared, that we take the 2 over, that cancels out, and we just have r. The derivative of the residual with respect to the activation, well, the derivative of this with respect to this is just -1, right? So we're treating this phi as the variable, y as a constant, it disappears, so that is -1. The derivative of the activation function with respect to the linear response, well, let's just call that value c, because that could change. And then finally, we have the derivative of the activation with respect to the weight vector, and that turns out to be the observation itself. So this is something that you have to have multivariate calculus for. This is just high school calculus. So the iteration is, we'll say that our estimate at k plus 1 of the weights is the estimate at iteration k plus some learning rate times the vector of steepest descent. And this is how it's most often written. That also equals, if we follow all of this through, what that equals is w at iteration k, and now the descent vector is this minus canceled out, and what we end up with is this is the learning rate eta times the residual for weight k times the derivative of the activation function at iteration k times we take the observation and we transpose it. And that is how it works. So if we have multiple data, multiple observations, I'll say, the way we handle this is the descent vector is just the sum of the descents that we get from all of the vectors. So the descent vector will be the sum as I goes from 1 to m to capture all of the observations, and this will be yi minus phi I, so that's the residual term, times, let's suppose that it's we'll leave this as a sigmoid activation of sigmoid I evaluated at the current weight vector times the ith observation augmented transposed. And so for a single data point, we have this simple iteration. And when we have multiple data observations, what we do is we say that the descent vector is the sum of the descent vectors that we would compute for each of our individual observations.